Section: Introduction and Literature Review. Introduction and Literature Review. The development of large language models, LLMs, like GPT-4 has brought about a significant change in the field of artificial intelligence, providing exceptional abilities in natural language processing. However, these models require a lot of computational power, which presents challenges in terms of cost, latency, environmental impact, and reliance on cloud computing. This has led to an increased interest in methods to optimize these models, particularly model pruning, to overcome these challenges. Model pruning, as discussed by #1510.00149, in their work titled Deep Compression, Compressing Deep Neural Networks with Pruning, Trained Quantization and Huffman Coding, is a promising method to reduce the size of neural networks without significantly affecting their performance. This method involves systematically eliminating non-essential weights from a network, thereby reducing its complexity, size, cost, and latency. Further advancements by #1803.03635, in their work titled The Lottery Ticket Hypothesis, Finding Sparse, Trainable Neural Networks, introduced the idea of identifying and training sparse sub-networks within larger models, suggesting that these lottery tickets can achieve similar accuracy to their dense counterparts. This paper explores the use of contextual pruning to create Mini-GPTs, which are smaller but efficient versions of existing LLMs. By analyzing and removing less important weights specific to different domains, such as law, healthcare, and finance, we aim to maintain or improve model performance while significantly reducing size and resource usage. This approach can be combined with those designed by #1510.00149, such as synapse pruning, or connection pruning, quantization, and neural architecture search. The initial motivation for pruning based on context came from the observation that modern open-source LLMs are trained on broad datasets, e.g., Wikipedia, commercial free books, and Reddit, but B2B users are only using a small portion of the information in the network that's relevant to their use case. For example, an LLM used at a hospital doesn't need to know about options trading and Shakespeare. It just needs common sense, logical reasoning skills, and healthcare domain knowledge. Methodology. Our methodology for developing Mini-GPTs through contextual pruning primarily focused on linear layers, activation layers, and embedding layers. We also considered various datasets and models. This section highlights these choices. Data. Our data collection focused on diverse domains to ensure a comprehensive evaluation of our pruning methodology. They are listed in table. The belief is that the more dissimilar two datasets are, the more differences in neuron importance we'll find, and then therefore be able to prune. Initial model selection. We selected GPT-like architectures due to their robustness and popularity in various NLP tasks, including machine translation and multiple-choice question answering. Our base models, highlighted in table, are pre-trained transformers built by Microsoft, Phi 1.5, or Meta, Llama 1.3 and OPT 1.3, and they each came with a customized byte pair encoding, BPE, tokenizer in Hugging Face. Contextual analysis for pruning. We conducted a detailed analysis of neuron outputs across linear layers, activation functions, and embeddings. This analysis helped us identify the weights that were less crucial for maintaining performance in specific domains. Linear layer pruning. To prune the linear layers of an LLM contextually, we monitored the neuron outputs and calculated, for each dataset, the normalized L1 norm of each neuron. This is shown in equation 1 where A_J_B is the JTH neuron of batch B, M_J is the JTH activation's average magnitude across batches, and epsilon_T is our pruning threshold. Figure 1 conceptually shows how this impacts pruning by looking at a basic linear layer computation. When normalized across input batches, if the L1 norm is close to the pruning threshold, then we prune the corresponding unused rows in the transpose weight matrix, shown in red. Similarly, when normalized across output batches, we identify which columns in the transpose weight matrix to prune, since they are not being utilized due to neuron synapses interaction. In Figure 2, we show example output of L1 norms for each neuron normalized for two datasets. Blue scatter points that fall below the orange line mean the neurons were activated more heavily in the first dataset as compared to the second dataset, and perhaps could be pruned from dataset 2. Activation layer pruning. This pruning targeted the activation layers, where non-essential activation neurons are identified and removed. As shown in Figure 3, the approach is very similar to that of linear layers. One main difference is that we only look at the outputs of the layer, not the inputs. The other difference is that we must look to the previous layer to prune the weight from. If the normalized L1 norm of the activation neuron is below the pruning threshold, then we prune the corresponding column in the transpose weight matrix of the prior layer. In the three models we looked at, this was primarily done to JLU and ReLU layers. Section Summary. The Introduction and Literature Review section discusses the challenges posed by large language models, LLMs, in terms of computational demands and the interest in model optimization techniques such as model pruning. The paper explores the application of contextual pruning to create smaller yet efficient versions of LLMs, specifically focusing on linear layers, activation layers, and embedding layers. The methodology involves analyzing neuron outputs and identifying less crucial weights for specific domains, and the pruning process is applied to both linear and activation layers based on normalized L1 norms. Section: Embedding layer pruning. We've developed a method to trim down the embedding layers, along with the corresponding language model head layer. This is achieved by assessing the frequency of tokens in a specific dataset. Although this method is effective, we've found that it requires large calibration sets to confidently determine if a token is truly unnecessary. One way to do this is by comparing the token frequency curves across different domains. Now, let's discuss the evaluation process and results of our smaller versions of GPTs after contextual pruning. We use two main metrics for evaluation: perplexity and multiple choice question, MCQ, testing. Perplexity is a measure of how well a large language model can predict the next word given a context. It's a standard metric in assessing a language model's performance. Generally, a lower perplexity indicates a better model. From our data, we noticed a decrease or no change in perplexity across all datasets after pruning and fine-tuning. This suggests that the models were able to maintain their performance in their respective domains despite having fewer usable parameters. We also evaluated our models using 100 domain-specific MCQs to further ensure that the model retained its ability prior to pruning. Since only one model, PHI 1.5, could generate a string containing the correct answer choice, we decided to keep the evaluation consistent across all models. We did this by selecting the question and answer string combination that resulted in the lowest perplexity, effectively using the model's best guess. The results showed that the pruned models performed comparably and, in some cases, better than their unpruned versions, demonstrating the effectiveness of our pruning methodology. To push the boundaries of our pruning methodology, we also tested a linear and activation threshold of 0.1. From our data, we found a potential size reduction of up to 41.884% with the phi model while maintaining the same perplexity as before pruning. However, the results suggest that we are nearing the limit of pruning for these models. For instance, the opt model struggled to maintain the same perplexity as before pruning, and the phi and llama models took tens of epochs to recover where only one was necessary in the 0.001 case. Moreover, looking at the MCQ results for each model, we noticed that accuracy decreased again after fine-tuning while the perplexity on the fine-tuning set decreased, indicating overfitting. Further testing is needed to determine if this can be mitigated with a larger, more representative dataset for each category or if this level of size reduction is too extreme. The results on the much larger English to Taiwanese dataset suggest the former, as MCQ accuracy increased across all models after fine-tuning.